So it is actually the top of the hour. Let's go ahead and let's get started. So my name is Andy Rivens. I'm a product manager for database and memory. I also have with me Maria Colgan, SQL Maria, who also database and memory is near and dear to her heart as well. And this is the AskTOM Database and Memory Office Hours, our first try at this. So be patient with us, but we'll try to get all of your questions answered. Our topic was going to be configuring the InMemory Column Store, but we're really here to answer any of your questions about database and memory. We've got your lines muted. So as Maria said, please, if you have questions to ask, just type them in the chat. And I think she's going to be moderating for me, since it's hard to do two things at once. Remember, we won't be answering any SR type questions. If you have support requests or licensing issues, that's not what we're after. We're really going to try to help you with your technical questions about database and memory. And so I thought Maria, did you have anything else you wanted to add?
No, that sounds about right.
Okay, well, we're just going to tag team this. So what I thought we'd do is, rather than doing any kind of slides, that doesn't seem really kind of appropriate for, whoops, I lost the share. What I thought I'd do is I would show you how to configure the column store. Well, I have a 12.2 database. I assume you guys can all see the screen here.
Yeah, you're good, Andy.
Great. And I have a 12.2 Oracle database, and it's already up and running. So you can see we have roughly a 400 gigabyte SGA, but notice we don't have, it just looks like a normal database. So what I was going to do is show you how to actually set up the column store. It's actually very simple. So let's do show parameters. Whoops. Like, the problem with this is it's not scripted, so you got to watch me type. But show parameters in memory. So these are the in-memory initialization parameters. In-memory size is the one we're actually interested in, and is really the only parameter that you have to change or set up to take advantage of database and memory. So database and memory first was introduced with 12.102, obviously part of 12.2. I think we might have a couple teasers for you about 18C, but it's all fully integrated into Oracle database, so that's all you have to do. You don't do anything different with the installation. You don't have to do all you have to do is have enough memory to support the column store. And so what I'm going to do is I'm actually going to go ahead and we'll just allocate some memory to the column store. So in-memory underscore size is the parameter we care about. Let's give it 200 gigabytes. And so initially, when you allocate the column store, you do have to recycle or bring the database up and down and then back up again. Actually, starting in 12.2, you can actually resize and increase the size of the column store, but you still have to initially allocate it.
And Andy, is there anything I should be mindful of when I'm picking that size for the in-memory size, other than, of course, that I have enough DRAM on the box? Is there anything else I should be mindful of?
Yeah, great question. So you do have to have enough, since the in-memory column stores, we'll show you once we start it back up, does take memory out of the SGA. You do have to have enough memory in the SGA to allocate the column store. And we tend to, in our best practices presentations, we say, don't steal memory from, say, the buffer cache or the shared pool. So you really have to think of adding additional DRAM or additional memory to the SGA to accommodate the size of the column store. In this case, I don't really have anything else running in the database, so I'm going to take half of my SGA size and allocate it to the column store. But if you had a running database with actual applications, you could severely impact your workload or your the performance of your applications if all of a sudden you took away 200 gigabytes from an actively running database. You really need to think of adding additional memory. That's kind of the in-memory part of database and memory.
Okay, so it's coming out of my SGA, and just make sure I don't starve any of the other components. All right, good.
Exactly.
Good.
My shutdown takes a little longer, but now we'll be able to start it up, and let's see what happens. So actually, the startup, once we allocate the column store, the database isn't unavailable. We don't have to do anything. We just allocate the memory as part of the SGA. We're seeing here this in-memory in-memory area of 200 gigabytes, but the database is up, running, available, and we haven't populated anything, but all of that happens in the background. So all you do is set the in-memory underscore size parameter, and the database acts just like it would if you didn't have it there, as far as startup, memory usage, all of those issues. So now we see that we have this in-memory area now allocated with 200 gigabytes. So that's actually how simple it is. That's literally all you have to do. What I was going to do, I have a few notes here so I don't forget what to show you. I wanted to show you, so how do you tell that it's allocated other than looking at startup, or maybe you do an show SGA? Wouldn't be data or Oracle database if we didn't have $v views, if we didn't have hints, we didn't have all of the normal statistics. So there is a $v view for you to basically select from to see how much memory you have allocated to the column store. So I'm a little leery that my formatting is going to be off here, but the view is actually in memory underscore area. Since I can't talk and type at the same time, a little pause there. So actually what we see now, what's interesting about this is actually a multi-tenant database. So I actually have installed in there 2 PDBs, but you'll see that for each container ID, if you will, the size is the same. We have a 1 megabyte pool and a 64K pool. So the 1 megabyte pool would be the IMCUs or the actual columnar formatted data. We haven't used any of that because we haven't populated anything. And then the 64K pool is for metadata. And we see that each of the containers sees the same amount of memory. And since it's a $v view, it's the CDB or the root, well, actually, that's not, yeah, CDB root that actually has the memory. And we'll kind of go over a little bit about PDBs and talk about if we wanted to populate data between different PDBs. Actually, I had another query for you to actually show you the PDBs we have defined, which is why I always try to write this stuff down so I don't forget what to tell you guys. Oops. So there's also a $v view, $v PDBs, where you can see what PDBs you have. I didn't format that very well, but we see that we have Cloud P1 and Cloud P2 are both PDBs, and so those are, we don't see it actually, oh yeah, the container name, and those are the container ID 3 and 4. And what I was going to actually do then was connect to, we'll use Cloud P1. So remember to go to the right user ID so we can actually populate some tables as well. Now, one other interesting thing about, oops, show parameters, PDBs, and if you're not in a non-multi-tenant database, it's just as it always would be. It's just a single instance. You show SGA or show select from $v views will just show you the default instance. You don't have multiple PDBs or multiple instances running. But since Oracle's recommended installation now is 1 PDB, and then I have actually 2 PDBs, so I can show things like this. Notice that our in-memory underscore size parameter, now we're connected to the DBIM user ID under Cloud P1 or one of the PDBs, actually has the same in-memory size as what I set it to in the container database. Now you can actually reduce that size, but that size by default will be the entire column store. And so let's actually, what I had wanted to do was let's populate something. So we've configured the in-memory column store. That's literally all you have to do is set the in-memory underscore size parameter and recycle the database. So that's pretty simple. And then, well, it doesn't do us any good if we don't have any objects populated. So how do we populate an object? And we can do this. Let's see what tables we have. So I have our traditional star schema benchmark set up in this DBIM user ID. And so what we'll do is we'll populate the line order table. It's not very big, but populating a table, we can support tables, partitions, subpartitions, or materialized views. We can, it's as simple as an alter table command. So alter table line order. Got this, yep. In memory. So I took the defaults for all of the parameters. That's literally all you have to do. So with a default of priority of none, I'll actually select from that table to begin the population of the line order table. I could have set a priority, which would have said begin populating essentially immediately. That would be something you might do in a production system where if the database were to go down and come back up, you would certainly want those objects to be populated as soon as possible. So you might set a priority, and then that can control, the priority then can control which objects would be populated first. We support critical, high, medium, and low, and then obviously the default, which is none. So let's go ahead and select from that table. But the database was open originally. It's still available. I'm able to select and do all of the normal commands or an application could run. And what happens is in the background, hopefully this will all work. Yep. We have these, see these Aura W processes at the top of our, this is just the top. So this command lets you see the processes in the Linux operating system and what's running. And we see that we have a whole bunch of these Aura W processes, and these fired up, they run asynchronously in the background, like log writer or database writer might be running, and they actually do the population of our table. And since I altered that table line order to be in memory, and I selected from it with, so it's now going to be populated. And so you see that all of these worker processes, I have actually a fairly big machine here, and so I have a whole bunch of worker processes set up. By default, you have the CPU count divided by 2. So you can do this on your laptop. I run this on a database on my laptops and sometimes do that for conferences. Or on your regular production machines, you obviously would have more resources. Now we see that all those worker processes are now gone. So we can assume, and let's see if it's true, that we populated all of those objects into the column store. Now I'm going to cheat and use a script I have. I'll show you what it does, so I don't have to try to type out the SQL query. But we see that our owner, DBIM, segment names line order, and we now, bytes not populated. Now that's a key attribute of the view. Let's look at that SQL real quick. So notice we selected from, I use $IM segments. In this case, we're not rack, but we could just look at $IM segments. But notice I just queried a couple of the attributes of that view. And notice that we have bytes not populated is set to 0. That's really what you need to key in on to understand that the object's fully populated. Did you have a question, Maria?
I did.
Okay.
You can tell by the look of my face.
I did.
So, now that you've got it populated, the question was actually about the size of the in-memory column store. And in a PDB, you mentioned there in a PDB CDB environment, the parameter is set at the CDB level and that all of the PDBs see that same size. And the question came in from Shri asking, is there any way that I can basically spread it across the PDB so everybody gets an equal share? Or can I do something else to make sure that one PDB doesn't steal everybody else's in-memory column store allocation? So can I manage basically the column store across the PDBs? And
the answer is yes. So you can set the in-memory size on each PDB to be less than the total amount of memory, and that way it'll be like an upper limit or a cap on each of the individual PDBs. So maybe our Cloud P1 PDB, I could have set it to 100 gigabytes, and then I could have set the PDB2 or the Cloud P2 that I showed you, I could have set that to 100 gigabytes, and then that way they don't interfere with each other. We can carve out the memory for each PDB. Now, an interesting side note to that is that you can actually over allocate the memory or the in-memory size on a PDB And the motivation there is, what if you were to, say, unplug one of the PDBs and you didn't want to have to restart the other PDB to take advantage of the memory that PDB that you unplugged was taking up. Now that becomes less of an issue in 12.2 because we also now support in 12.2 the ability to dynamically resize the column store and make it grow larger. So now there's less motivation than there was when we were on 12.102 to do that, so that you can actually give each PDB just the amount of column store that you want, but obviously you're limited by the total amount of memory that's been allocated in the container database.
Cool. Okay, so then I can limit by setting the in-memory parameter on a per PDB basis. So in fact, one of them could have 0, right? So that they don't use the column store at all if we wanted to. Okay, great.
Yep, absolutely.
Thanks, Andy. I think that's it.
Okay, and so now we've literally populated our line order table into the column store. A little tongue twister there. Let's just, as a kind of a wrap up, we said we could look at the amount of memory we've allocated in $v in memory. So let's, I'm trying to talk and type at the same time. So now we see that we do have space used in our column store. So we still have our total of 200 gigabytes divided between the 1 meg and 64K pool. And we've used up, what is that, almost 40 gigabytes for the line order table.
Andy, is it true to say that if the object, the line order table, is 40 gigs on disk, it'll take 40 gigs of that 1 meg pool?
No, it's not. So actually, we didn't get much compression on our line order table, unless I'm not looking right. There's actually multiple levels of compression. Typically, we get anywhere from 2x to 20x compression rate. Actually, I know I forgot about that. So in my, so this is actually taken from a hands-on lab demo that we do. And so I've actually compressed the line order table with basic table compression. And I didn't think about the fact that that's actually why you notice the bytes, which is the size on disk, and the in-memory size are just about the same. And actually the trick there is that we already get, when we do on disk compression, which is completely separate from in-memory compression, we already get about a 2x compression rate on the line order table. So it looks like we didn't get any compression. And I'll have to remember to, usually I highlight that with a script in the hands-on lab. For this purposes, though, we got tripped up in not realizing that we weren't going to actually see the compression. But very often, the default compression level, mem compress for query low, usually gives us anywhere from like a 2 to 4x compression rate. It is somewhat data dependent, but people usually see at least 2x compression. And then at the higher levels, like the 4 capacity options, we get a much better compression rate from 10 to 20x is very typical.
Okay, so as long as I don't have it compressed on disk, I should see it to be smaller in memory than it was on disk.
Right, but because that bytes field is just showing us what it is on disk, and since we don't, we don't try to guesstimate that if we decompressed it, it would be this size. We just see what's actually there.
Right. Okay.
So that's a little flub on my part, I guess, for this demo, but it usually works well when we're working on like laptops or virtual boxes where we need to consolidate as much data as possible and compress it. And of course, customers use advanced row compression and compression all the time. So it's good to know that all of that's very seamless. Compression on disk, compression in memory, even though it's different, it's fully supported, works seamlessly.
Cool. And
that's about all I had, actually, for the demo.
So I've got a couple of more questions for you then, if that's okay. Yep. So, for example, there you gave us, you mentioned that we could populate a table or some partitions. Can I populate views into the in-memory column store?
Great question. So you can populate materialized views, but we don't actually populate views themselves. So because if you think about it, a view doesn't have any persistence. It's really just a SQL definition. And so we certainly can populate the underlying objects because they have persistence. So if you can actually populate, if you think about it, any view that you would like, because all you have to do is populate the underlying segments as that are being queried from that view. One of the other kind of cool things about database in memory is you can actually selectively populate only certain columns. So you can exclude columns from the population. So if your views that you want to have populated are only accessing certain columns, you can actually restrict the amount of memory you're going to use by only populating the columns that are actually going to be queried in your analytic queries. Obviously, materialized views, though, do have persistence, so you can fully populate a materialized view. And I think I said earlier, also tables, partitions, or subpartitions.
Great, okay. And what if I mess up and there's 3 tables in my view, 2 of them I've remembered to put in memory, but the third one isn't there? Can I still get some benefit from the column store?
Sure, because we'll access the tables that are populated in the column store, and then the other table we'll access from the row store. And so it'll combine the access between the 2.
So, great.
And actually, that brings up, I kind of go for my, all my presentations that I do and I talk to customers, and that means also that if the table's not fully populated, say we didn't have enough memory allocated in the column store to fully populate our line order table. Maybe we only had allocated 20 gigabytes and it takes 40 gigabytes. So what happens then? Well, we populate as much memory we populate as much of the table as we can into the column store, and then any data that doesn't make it in the column store we'll access from the row store. But your application or your SQL statement won't get an error. It just won't be as fast as if it was fully populated.
Okay. So one of the other questions I had was, you showed us those worker processes and you mentioned that by default I get the number of worker processes is controlled by the CPU count divided by 2. How do I change that if I wanted to have more of them?
So that's the cool thing about having our terminal up here. So that's actually controlled by this parameter here, in-memory max populate servers 40. So I actually didn't change that. This is actually a pretty big machine, and it has 80 CPUs.
Ooh.
I don't know if that translates to 80 CPUs or cores, but anyway, so it got set to 40 because that's the CPU count divided by 2.
Okay.
And then that's dynamic. So you could actually increase or decrease that parameter. For instance, if you had set priority on your objects so that when you start up the instance, you want those objects to be populated, you could actually increase the in-memory max populate servers to a higher value to try to get that population to happen sooner. As we saw from the top, population is a pretty CPU intensive process. So if you allocate more of these max or populate servers, it'll populate faster. And then you could actually then bring it back down to the default after the population is complete so that you could do normal workload for your applications. So
hold on, you mentioned priority and you mentioned these processes. So the higher the priority, the faster the populate occurs? Is that what I heard?
No, that's not the case. So priority only controls actual population. So it doesn't do me any good to show you the line order table because it's actually a default of priority none. But we actually have multiple priority levels, but it only controls the order in which we begin the population.
Okay.
And then priority doesn't come into play for things like queries. We don't query a table that has a priority of high before we query one that has a priority of low. It's only concerned with automatically starting the population and then the order in which we populate the objects.
Okay, so it doesn't control the speed. And if I want to control the speed, it's this in-memory max populate servers. The more servers I have, technically, the faster it could go?
Right, up until you hit your maximum CPU limit.
Okay,
the max
so
capacity,
kind of
CPU capacity.
Yeah.
Right.
Between CPU and the speed of populate. Okay. Now, once something's in there, if I started loading other things in, and does Oracle just age out the oldest blocks, the least recently used, just like what I have in the buffer cache?
No, that's why we call it a column store. So I like to tell people that in-memory is really an enabler. The database in memory is all about analytic queries and the columnar format of the data. So we actually populate the entire object into the column store, and unlike the buffer cache, it stays fully populated, like our line order table will stay fully populated No matter if you say we filled up the column store and we'd ran out of memory, it wouldn't like page out or remove some of the data for the line order table. It's going to stay fully in memory. Of course, that's how we get the speed. We don't want to have to wait to go to disk, since we're scanning all of these columns very, very quickly. We want it to be in memory to enhance the performance. So it's the store, not a cache. And a lot of people kind of mistake that, because let's see if I can go back up to our SGA. So notice here, our database buffers, the buffer cache, it is a cache, right? We don't have to have all of the data populated there, but with the column store, it's a store. And so once you've populated an object into the column store, until you do an alter table no in memory, or stop the database, it won't. That object will stay in memory in the column store.
So we got another question, and this time it is: does InMemory manage updates as well as retrievals? So if I'm doing an update, it makes sure that the memory and the DB the InMemory and the database are consistent. Is the question that we've got? Right.
Yeah. So people ask that a lot, and right, we keep it transactionally, simultaneously consistent and transactionally consistent, basically the same way we do an index. The advantage for database and memory, though, is that there's no persistence. The data is pure in memory, so we don't generate any undo or redo. And so not only do we keep it transactionally consistent, but it's a lot less overhead to do that than it is to keep an index up to date, which we also do when you do changes of column values, and those column values are indexed. So you can kind of think of the column store as being all the columns are essentially indexed. So it's not quite the right analogy, but it's close. And you get to do it with a pure in-memory structure, so you don't have to worry about keeping recoverability, basically. So the row store is always the persistence, the source of record, if you will. And all recoverability is always generated by the row store or governed by the row store. And so since database and memory is a pure in-memory format, we don't change any of the on-disk format. So all of your existing Oracle technology like RMAN, Golden Gate, DataGuard, none of that changes because we haven't changed any on-disk formats. A little tongue twister there.
Neat. Okay, so I'm always going to get the right answer if I go to the column store, even if the data in the database is constantly changing due to DML updates, inserts, deletes. I'll always get the right answer from the column store, right?
Right, and even if it's not populated, if part of it, our example before, where part of it might be populated and part of it not populated.
So no concept of dirty reads in Oracle, always consistent. Always.
We couldn't do that to our customers, because that's kind of what our bread and butter has always been, is about read consistency and not having to manage any of that, unlike some of our competitors.
Awesome. Okay, I've got another question for you now in the chat. Do the tables that we add to the InMemory Column Store persist across a database restart? So how does that work, the content of the column store, if I restart? So they don't. The column store is a pure in-memory format. If we bring the instance down and bring it back up, we have to repopulate those objects into the column or into memory in the column store. It's actually the same thing we have to do with the buffer cache. Just you don't tend to see that as it's not as obvious, because we're typically only caching a very small portion of the table. But even the buffer cache, the same is true. Now in 12.2, we introduced a new feature though called Fast Start. And what that does is allows us to checkpoint the contents of the column store to disk in order to be able to restart faster. So since we do have to repopulate the column store into memory, that's the in-memory part, we have to take that row format, here's my hand motion, into columnar format, and we compress it, we add our storage indexes. We can avoid some of that work by, if you choose to use the feature Fast Start. And we'll actually checkpoint the column store contents onto disk, so that if we need to restart, we can actually read that data and avoid some of the formatting that we have to do to translate the data from a row format to a column format. Okay, and is there anything I can do to determine which objects get into the column store first? So if I'm if I restart my database, my buffer cache is empty, as you said, as I start to run queries, the objects I'm touching in those queries are populated into the buffer cache automatically for me. Can I manage what goes into the column store on a restart in any way?
Well, only through priorities. So you can set priorities. And then actually, if you have objects that have a priority of none, as soon as they're accessed, then they'll jump into the queue as well to be populated. But the only way to control which objects are populated first is basically by setting a priority. Again, we go from critical to high to medium to low, and then the default being none.
Okay. So what will happen is when the database restarts, it looks at the objects that have an in-memory attribute and a priority, starting with high, and then it goes on to medium, and then to low. And in the meantime, if I happen to touch any of the objects that have no priority, they'll also start to get added to that queue. Is that right?
Yeah, actually, any object you touch, I guess, even if it has a priority, it'll get bumped up if you've accessed it. So yeah.
Okay. Great. All right. So you mentioned earlier on too about the sizing, that I can grow my in-memory column store on the fly starting in 12.2. Can I shrink it as well, or just grow? How does that work?
Yeah, no, you can't shrink it. You can only increase the size of it. So I guess we could try it. But we currently have our in-memory size set to 200 gigabytes, which is the most we have. But if we had it set again to like 100 gigabytes, we could actually say alter system, set in-memory size to, it's got to be at least 128 megabytes larger than the existing size. But we could have set it, say we had it at 100 gigabytes, we could then say set it to 150 gigabytes. And then that would actually dynamically, right on the fly, without having to stop or start anything, it would size it larger. So it can only size as large as the amount of memory that you have in the SGA. And obviously, if you already have space allocated to the buffer cache and the shared pool, although if you have automatic shared memory management or automatic memory management, you could steal some memory. It could come from the buffer cache, which it would if it's not being used. But you have to be a little careful with the resizing, and it's typically meant for like emergency situations where an object has grown. You don't want to take an outage to stop the database and restart it with a new parameter size. We just need it for a short amount of time, or until we can take an outage, to really allocate additional memory and allow you to kind of get by without taking an interruption to your service. But we only support growing the column store, not decreasing the size.
Okay, great. So then we also got a question actually offline. So I don't know whether the folks realize this, but in office hours, when you register for the office hours, you can also submit your questions ahead of time. And one of the questions we got ahead of time, Andy, was about DML. Can I use the in-memory column store to speed up updates or not?
Yeah, so the column, so inserts, updates, and deletes are actually performed on the row store, and then we reflect those changes in the column store, like I said earlier, similarly to the way we do keep an index up to date. So database in-memory actually won't speed up inserts, updates, and deletes, or DML activity. Now, if you think about it, since the column store is providing the analytic access, very often you can remove a lot of your analytic reporting indexes that you've had to put on to support reporting or ad hoc type queries. And so if that's the case, then you technically can get a capacity advantage or by dropping those analytic reporting indexes, but the actual DML activity itself is not going to be sped up. Database in-memory is really all about analytic queries. In one of we'll have more themes with the database in-memory. I think one of them will probably go over execution plans. And in an execution plan, you'll see database in-memory table access in-memory full. And what that means is we're actually scanning all of the columns for the object that are part of that query. And so it's not like an index access where we might do a row ID access. And so that's really the focus of database in memory, is that analytic workload, as opposed to OLTP workload, which is typically inserts, updates, deletes. Obviously, there are some selects which the optimizer may cost, because it is a cost-based decision on whether we access the column store or the row store. And so even in an OLTP environment, you may have like what we call a mixed workload environment, where you're still running some rather large, say, analytic type queries after data has been changed. And so the cost-based optimizer might still choose to use the in-memory column store, but for the actual inserts, updates, and deletes, we're not going to speed those up.
All right, you might be sorry that you mentioned the word optimizer there, because we're getting some questions now about how this interacts. And I know—
well, that's why we have you here.
We're going to have an extra session in more detail on this as we go through the coming weeks and months with these office hours. But let me ask it anyway. Does the optimizer statistics on the table influence the in-memory performance at all?
It does. The table statistics don't, well, actually the optimizer, as it does it, since it is a cost-based decision, you don't say select from the row store or select from the column store. You just say select from, say, the line order table. And so the optimizer, so you still have to have, for the optimizer to create an accurate plan, you still have to have statistics associated with the line order table, just as you would without in-memory. But in addition to that, the column store at parse time will actually calculate some of the statistics about the object in the column store, like maybe the number of IMCUs, the number of rows that have been changed. If there's a certain amount of the data isn't populated, there's a bunch of those kind of statistics that are kept track of by the optimizer and used as input to the costing plan. You don't control any of that. You don't have to say DBMS stats, gather in-memory stats or something like that. It's all automatic. But of course you still have to do, and of course most of that's automated even at the segment or the row store level, but it's still going to take input from both, because that's how it's going to decide, do I access the column store or do I access the row store? That's kind of the secret sauce behind database in memory, which is why you don't have to change any of your applications. Your SQL can run unchanged with database in memory and still take advantage of it. You don't have to make any of those changes or any application changes.
Nice. Okay, so it doesn't impact the performance necessarily, but the optimizer statistics influence the plan that is being chosen.
Exactly.
So I have a good representative set of optimizer stats, and then the in-memory column store will do the rest, and I should be okay.
Right. Exactly.
All right. Hopefully that addresses the questions we have there from Shri. Thanks for that. Any other questions you may have, don't hesitate to use the chat option. You can send them to me directly or to send them to everyone. I'll get to see the chat, and we can help address those questions. One of the questions I had just looking at what you've got on the screen there, I noticed that we're carving off a piece of the in-memory column store away from where the data is stored in the 1 meg pool to this 64K pool. Can you give us a little bit more detail on what goes on with that 64K pool?
Sure. When you populate an object, let's take our line order example.
Yeah.
We allocate something called an IMCU, or an object will be made up of one or more IMCUs, or in-memory compression units. And you can think of those like extents. So we're going to allocate or take a bunch of rows. We're going to read it off of disk. We're going to reformat those in the columnar format. We're going to compress them. We're going to add our storage indexes, and we're going to add that to an IMCU. So an IMCU, so our line order table will be made up of one or more IMCUs, and those IMCUs are made up of one or more of the 1 megabyte memory allocations within the 1 meg pool. So that's where we see we have basically our 40 gigs from our in-memory size. It's roughly the same. And then what we'll do is we also have, for every IMCU, we'll have metadata, a metadata unit or an SMU, a snapshot metadata unit associated with that IMCU. And that keeps track of things like changes. So we had the question about DML and what if I change certain column values, how does the column store keep that in sync? And so we mark that information in these SMUs or the metadata units, and that comes out of the 64K pool. Now you can't change these allocations. We do all of this automatically for you. All you set is the in-memory_size parameter, but this is so that when we have lots of DML, we have the ability to have enough metadata to keep track of all of the changes. And then in the background, we'll be repopulating that data as changes occur, so that for the most part, you'll access data that is unchanged or that reflects exactly what's in the row store. Any of the data that is changed, any of the column values that are changed, we will always get those from the row store so that you always get that read consistent view.
Great. Okay. So we got another question for you. This one involves row level locking and concurrency. So the question is the row level locking and so the concurrency influenced or limited in any way by the table being stored in the in-memory column store? As an example, there is a limitation if there is a bitmap index on a table for row level locking, but do we have any such limitations with the in-memory column store?
So the answer is no. Since it is a pure in-memory format, so we're not changing, these IMCUs that reside in this 1 megabyte pool are really read-only. So we're not changing any of those values, because if values were to change, those values would be changed in the row store. So all of the row level locking and those concurrency issues are still, they haven't changed as far as the row store is concerned. But in the column store, we don't have to take any of those kind of locks. So we have no real concurrency issues within the column store unless we want to talk about population itself. Obviously, if we're populating, then we have to serialize on the population. But once that's complete, then there's no concurrency issues as far as the column store itself is concerned, which is why we can handle very large queries against the column store and be able, basically all it is CPU and memory access. And so it's very efficient.
Great. Okay. So I've certainly no concerns about putting an object into the in-memory column store and worrying about impacting the row level locking.
Yeah, and actually it's actually much less overhead because we don't have any undo or redo, or we don't have to do any of that like we would if we had indexes, if that data was indexed. So it's actually much lower overhead in general having the data in the column store and being able to reduce the number of indexes you have to maintain.
Cool. So is it possible to say then that in-memory may improve the performance of my DML operations if I'm able to delete some of those reporting indexes and not worry about doing the redo and undo for managing all those indexes?
Yeah, sure. The overhead of maintaining those is, and actually, even though indexes are very efficient, they do take quite a bit of overhead when they're changed. And they take more effort, more resources, I guess is a better way to put that. The technical term would be resources, than it does to actually make the table change itself. And so by reducing the number of indexes you have to maintain on tables, because those indexes presumably are supporting analytic workload. Again, we're not talking about things like primary keys and foreign keys and referential integrity, or even typically small lookups where you're accessing just a few row IDs. Those kind of indexes you're going to have to maintain for your application's performance. But the indexes are being used for analytic reporting where you're scanning large amounts of data. Most of those can go away because the column store is going to take over that functionality. The optimizer is going to choose a table access in-memory full.
Nice. So I could actually also shrink my database then, right? If I can get rid of some of the redo as well as some of these reporting indexes, I could actually perhaps shrink the size of my database with the introduction of in-memory.
Actually, that's very true, because when we talk to customers, very often, especially for mature OLTP or mixed workload environments, there can be as much space allocated to indexes for a particular table as there is for the space the table itself takes up. So yeah, not only reducing the space required for the indexes because they are persistent, plus then all the undo and redo that's generated, and especially the redo, because then those goes into archive logs, and so then that has to be backed up as well. So yeah, you can actually reduce not only your resource overhead, but also space overheads considerably.
So I've got a question for you now that I know we'll have a separate complete office hours on this topic, but it's to do with the in-memory column store and rack. Let's take it now, but as I said, we'll probably end up doing a whole office hour session on just using in-memory and rack, because there are lots of things to consider in that scenario. But let me just ask you what's come up. It's in terms of population, which is why I think it's worth asking here. But imagine I've got a 2-node rack cluster and I lose one of the instances for whatever reason. And when it comes back, does it need to go through the routine of populating objects into in-memory or into memory again, or what happens during the loss and during the bringing that node back online?
Okay, that ought to be this will be a little lengthy. Yeah, short question. So let's use our example of a 2-node rack. Let's just go with a regular table. So we actually in rack, database in memory works as a scale out infrastructure. So we'll actually have a column store allocated on each of the instances since we have 2 nodes. And by default, for a normal table, we'll distribute those rows between the 2 nodes. So we'll get roughly half the rows on one table, or actually column values, because we're going to be populating those in the column store, and the other half of the data will be on the other column store. And then we'll access that data using parallel query. So we obviously, on a single instance, if you're connected, you can't access data on the other instance. Unlike traditional rack, we don't share the data. We don't have this idea of cache fusion. In order to allow us to be able to scale out, we want to be able to have, so if we had a 100 gigabyte column store on one node, we have a 100 gigabyte column store on the other node. We don't have 100 gigabytes of column store. We actually have 200 gigabytes because we don't share the data between the 2 column stores. And so to access that data, we use parallel query. Now, I'm going to get to the point where I'm going to forget what your question was, but if one of those nodes then has half the data that goes down, that's the question, right?
Right.
What happens? So if the node is down for a very short period of time, say, I think it's like roughly 2 to 3 minutes, it does vary a little bit, then nothing will happen and that data will be missing. A query will access half the data from the surviving node and it'll get the rest of the data from the row store. So the query itself will still run fine, it just won't have as good a performance. Now, if that node comes back up, then we'll repopulate the data, and once it's repopulated, it'll be like it never happened. If that node stays down for longer than that, and there's enough memory available in the surviving column store, we'll actually repopulate automatically that data into the surviving column store. Now all of the data will be in the one column store. And if that node were to then eventually come back again, we'll move that data back over, since our distribution will be by row ID, we'll move that data back over to the other column store. Now, just not to complicate things even further, but if you actually have Exadata in an engineered system, we can actually, and you had more than 2 nodes, say you had 4 nodes, you can actually duplicate the data so that it's mirrored, and you might not have any outage at all as far as data not being available in the column store, because you could actually mirror that data across the 3 surviving nodes. It's an alter memory or alter table in memory attribute on engineered systems. And so there's a lot of, it's funny because I tell people database in memory is very simple. All you do is allocate the in-memory size parameter, you restart the database, you alter a table in memory like we saw with line order table, and you're done. But there's always, with everything with Oracle, there's always these options and these little features and these other things that it's good to know because you can take advantage of certain things in certain environments. So that's my long-winded answer to your question. I think I got it there.
Based on the chat, I think they're happy with that. It certainly gives us an idea. But there is a follow-on question on that. So you mentioned that on Exadata, I have the added advantage of mirroring my data in memory, so that if I was to lose a node, we'd simply read the data that was stored in that, primarily stored in that node, from its mirror on one of the other nodes. But are there
Correct.
any other advantages of running in memory on Exadata that I would be worth knowing about?
You know, it's funny because the biggest advantage now is that with 12.2, this isn't actually a direct answer to your question, so I'll try to come back to that. But one of the huge advantages is that Exadata systems have large amount of flash, like terabytes of flash available. And in 12.2 now, we support the in-memory column store format in flash automatically. We actually did a blog post on all the different variations of that. Again, wouldn't be Oracle if we didn't give you lots of choices, but we can automatically now support terabytes, even if your DRAM is only 768 gigabytes per node or a terabyte and a half per node. If you have multiple terabytes of data that you would like to have in the column store, you can take advantage of flash. So that's probably, to my mind, that's the biggest advantage for Exadata. Now, I think where you were actually headed, though, was the duplicate option. There's actually two parts to the duplicate option. You can say duplicate, which will mirror the data, but you can also say duplicate all. So what that does is then it takes the object that you altered to be duplicate all, and it will populate that object in all of the column stores. So say we had an Exadata, more typical environment would be 4 nodes rather than 2, but then we'll populate the entire object in all 4 of those nodes. So think about, especially in Exadata, if you're doing a warehouse, star queries where you might have a dimension table and fact tables. Your fact table might be partitioned amongst all 4 of those nodes. So a partition in each of the nodes across, what I'm looking for the word is distributed across each of the nodes. So you might have, say, 20 or 30 or 100 partitions, and each divided by 4, each of those partitions will be across those spread across those 4 different nodes. But then the dimension tables could actually be populated within each of the nodes. And then you can do partition-wise joins. So you can actually do the complete join within each of the nodes on each of the different partitions. So there can be a performance advantage to the duplicate option as well. I don't know if that's where you were going, but that's what always pops into my head after the flash issue, which is actually a really cool feature in 12.2 to be able to do.
Yeah, no, they actually, all 3 seem like a really good benefit. I get to mirror my data to protect against any rack failures. I get to expand the volume of data I can store in the columnar format by taking advantage of the flash and getting all the benefits that I would get from the in-memory column store, which we'll talk about in subsequent office hours about how we improve query performance. But all those benefits are available to me down in the flash layer, and the volume of data I can store is greater. And then the third one, as you said, I can start to use some of those mirroring techniques to co-locate my joins within a single rack node, so I don't have to redistribute the data to do the join, and actually get a performance benefit there. So there are just 3 of the key advantages I get from running on Exadata. I'm guessing too that my population performance might be a little better on Exadata just because I've got the great storage, right? The smart storage. When I'm scanning and the data and populating into the column store, my I/O throughput on an Exadata is normally pretty darn fast. So I'm guessing my population performance will be pretty sweet on Exadata as well, over your standard commodity configurations.
Yes, and the Exadatas have so many CPU cores that the population has much more CPU power as well. So the combination of the 2 makes Exadata a great platform, very fast.
Awesome. Yeah, I'd also imagine too, if I do end up, as the rest of the query progresses, and I do end up having to redistribute some of the data to perhaps do a group by or something like that, the interconnect on the Exadata, the InfiniBand, would also help me out there, as well as making sure that I get pretty decent performance.
Right. Yep. Actually, we even have the direct-to-wire InfiniBand, so we've optimized the messaging that takes place on the rack system. So even that, it makes it faster. So not available on commodity hardware.
Yeah, it's neat. All right, so there's a couple more questions. They're coming in thick and fast now, so let me try and keep this going.
Well, we were worried we wouldn't have enough questions, so that's good.
I'm worried that we're going to run out of time now. But okay, so the next one, does the explain plan for the SQL statement show that it's leveraged in memory?
It does. Do I have a quick? I'd love to. I didn't think to actually have an example to do that. It does it. Oh, here we could just do
an
set.
explain plan for. Oh, you could do it with auto trace too.
Yeah, we'll just do auto traces can be, but yeah, no, this will be select. We don't want to select cat star. Oh, now if I could type, get all excited here about showing an example and forgot how to type. Yeah, so what you actually see is table access in memory full. So that says the optimizer intends to access the line order table from the column store. Again, it's a cost-based decision. The optimizer at parse time decides, is it going to access the column store or is it going to access the row store? And then in the execution plan, this is how you know that it's going to go after the column store.
All right, that looks great. So it's basically an indicator that some or all of the data will come from the column store, right?
Yeah, it's not a guarantee. It could be that not all of the data is populated in the column store. I'm trying to think of some of the other reasons that you might have to help me out being the optimizer lady, but trying to think of some of the other reasons. Typically, it's that we won't access it because not all of the data, so we'll access all the data that we can from the column store, but any data that's not in the column store, we still may have to access from the row store and any changed values.
Right, it's our intention that we'll get it from the column store or as much of it as we can from the column store. So it's a good indicator. All right, here's the last question that we're gonna have time for today. It's back to rack, and I'm not 100% sure I fully understand the question, so bear with me. If the column store is not shared between nodes in a rack environment, does this imply that a query executed on one of the nodes and requires also data stored in the column store from the other node will either access that data from the local instance? Okay, all right, so something we didn't mention, right? But there is the capability, if I'm not mistaken, Andy, that in a rack environment, I don't have to have an in-memory column store on all rack nodes. Is that true?
Yes, that's correct.
So how would I control it if I only wanted the in-memory column store on one node?
So if you only want the in-memory column store, so in-memory underscore size, of course. So you would set in-memory underscore size. Your question earlier was I would set in-memory size equals 0 maybe on one node, and on the other node I might set it to our 200 gigabytes that we had if we had a rack environment and we had that much memory. And so then the column store would be allocated only on one node.
Okay.
So then in 12.1 we actually have a series of blog posts, and as I recall, somebody guested for us and updated that with some of the more current information. But if you want to check our blog post in 12.1, it's a little difficult. But bottom line is it all revolves around using services and services to connect to either the instance that has the column store, or in 12.2, we can actually decorate the table with a for service clause. So then the population and the querying can occur even if as long as you're connected to that service, you can access that data from whichever node you're connected to.
Okay. So their question's a little different. So imagine, as you said, we've allocated an in-memory column store on one rack node. The other rack node has an in-memory size of 0. If I'm connected to the rack node that has an in-memory size of 0, and I issue a query that uses some of the tables that are in memory on the other rack node, do I go to the row store or the column store to answer that query?
And yeah, so I was trying to, it's complicated in 12.1. Yeah. So in 12.1, we'll actually go to the row store. So we won't be able to go across to get that data from the column store. In 12.2, you actually will get it from the column store. Correct me if I'm wrong. You did the most recent idea or paper on that, and because there we know this, we've associated the object with a particular service, so we know that we can connect to that object and get that data. So we don't have to go to the row store there. It's the 12.2's And we actually did this for Active Data Guard because we support Active Data Guard or the in-memory column store on a standby database. And the side effect is that it makes managing objects in different column stores or a different column store on a rack node much easier to handle.
Awesome. Yeah, no, that's it exactly, Andy. Thank you so much for taking the time to answer all of our questions today. That was fascinating. I learned a lot. Hopefully everybody online did too. And we'll be back again, right, in a month's time, Andy, to do another office hours?
Yeah, I think we're scheduled in March. And if you go back to the in-memory page, I think you can go ahead and sign in. Let's see, I guess I need to share that page. But if you go back to our office hours page, you can register. Yeah, it looks like it's March 14th, and you can register for that session. I think in that session, well, you kind of led, and maybe we'll, I don't know if we'll talk about rack or we haven't actually, I don't think, scheduled anything just yet, but that may be the next one up. We'll have to talk about it. And we'll actually, I think what we'll do is since we're scheduled for March and then it looks like April, we'll go ahead and publish out a topic. But of course, like we did today, you can ask any question about database and memory, and we'll be more than happy to answer that. If we can. If we can't, we'll find out the answer for you.
Awesome. Okay. And one last thing, there's been some questions about, the commands you used in the session today. Where's the best place to get more information? And my personal opinion would be the blog, Andy, right? The blog that you look after, blogs.oracle.com/in-memory.
In-memory, yeah.
The best place. And I'll put that on the chat for everyone just now. But that's where I would go. There you can get links to the white paper, as well as the best kind of our white paper on in-memory, but also a lot of the blogs have the same commands and that you used in the session today, as well as access to the white papers as well, and videos where you can get more information on what Andy's shown.
Right, and I kind of consider that our portal into all things database and memory. And actually in 12.2, the documentation, we have our own in-memory guide as well. But I agree. I think the blog is the best place to start, the best link to all of the different information we have, the white papers, and the previous blog posts. A lot of the things we've talked about today are in our different blog posts that we've done, and we're keeping them going. So I think that's a great place to start.
Great. Well, thanks again for your time, and we look forward to doing the next office hours.
Great. Talk to you guys later, and hopefully we'll see you in March.